Hello everyone, today I'm going to talk about the first sharper analysis of stochastic gradient descent for matrix completion problem. My name is Qi Jing. This is a joint work with Sham Kakeda and Prince Natrapati. So first, matrix completion problem is about if we have a true matrix M, which is low rank, and we want to recover this matrix by only observing a small fraction of its entries. And we are working on this online streaming setting where basically we assume each entry comes in sequentially, and we want to have an algorithm which have fast incremental updates. We're making two assumptions for this task. First is M is low rank and also incoherent. Second one is we're assuming each entry comes in uniformly sampled from the entire entries. So our algorithm is also pretty simple, which is just a standard SVD initialization plus stochastic gradient. If we're looking at update equations, we can say in each iterate, we're only updating one row of U and one row of V, which only take order K operations, and it's super fast. So the main takeaway of our paper is actually, so given good enough initializations, we can say matrix completion can be done by only one path through the data. So compare our results to previous results, we can first category all the results into two categories, like offline ones and online ones. And if we were looking at the total runtime, we see like in the offline setting, alternative minimization and projected gradient descent already give you a pretty tight runtime, which is already linear in dimensionality. But if we're looking at online case, the only guarantee for SGD actually is kind of like super slow in runtime because they incur high polynomial with respect to D. Our results is the first one, which should give you linear in D runtime. And if we look at the sample complexity, we see our sample complexity is pretty competitive even with respect to the offline algorithms. So the key part of analysis is we actually decompose it into two parts. The first part is basically saying locally around the optimum, and our objective function is both smooth and gradient dominant. And these two conditions already give you some linear convergence. And the second part is also the most important part is this entrapment statement, which kind of like saying once you get into this local region, you will continue to stay in this local region with high probability. So the challenge for this statement here is first, because we only observe one entry at a time, and we are doing stochastic gradient, and the noise in the gradient is actually super large. So the looseness in the previous paper is actually because they want to deal with this noise, and they could only allow super small learning rates. But we also know we want a fast learning rate, we want a fast runtime, so we also want a large step size. So these two requirements kind of conflict with each other. And this is also the hardest part in our paper. And we kind of like require super sharp analysis. We're giving this analysis by conditional supermartingale techniques. If you're interested into our results, welcome to our poster at NIPS. Thank you very much.